I am Yuya Digawa from Graduate School of Information Science and Technology, the University of Tokyo. I will begin our presentation entitled Accurate and Fast Performance Modeling of Processors with Decoupled Frontend. Researches on the instruction cache design, for example, cache replacement algorithms or prefetching, have focused on reducing the number of instruction cache misses. However, the correlation between reducing the number of instruction cache misses and reducing the number of executed cycles has decreased. This is derived from the front-end structure of modern processors. In a classical processor, branch prediction and instruction cache accesses operate in synchronization. So, instruction cache misses immediately stall the pipeline, as shown in this pipeline diagram. F is demand fetching, D is instruction decode, X is execution, and M is processing an instruction cache miss. By contrast, in a modern processor, instruction fetching continues even if an instruction cache miss occurs. This is because the modern processor has a queue called FD queue. Before demand fetching, there is a P stage, where instruction fetching is done according to the address in the FD queue. The latency of the first miss hides the latency of the subsequent miss. Thus, the increase in processing time is mitigated. To see the impact of such modern processor behavior, we investigated the relationship between a reduction in instruction cache misses and a reduction in executed cycles when applying an instruction prefetcher (RDIP). Each point in this figure represents a workload. As you can see, some points are distributed around the horizontal axis in this figure. This result indicates that reducing the number of instruction cache misses does not reduce the number of executed cycles for some workloads. To clarify the relationship between instruction cache misses and performance in modern processors, we focused on the relationship between instruction cache misses and branch mispredictions. Hiding the latency of instruction cache misses explained before is effective until the next branch misprediction. Based on this observation, we consider one branch misprediction to the next branch misprediction as a region. As these pipeline diagrams show, the number of executed cycles depends on whether or not there are cache misses in the region. We call a region not containing instruction cache misses a hit region, and a region containing one or more instruction cache misses a miss region. Based on these insights, we found that the number of executed cycles can certainly be reduced by reducing the number of miss regions. The left figure is the figure I showed you before. This figure shows the relationship between a reduction in instruction cache misses and a reduction in executed cycles. Similarly, the right figure shows the relationship between a reduction in miss regions and a reduction in executed cycles. As you can see, a reduction in miss regions is highly correlated with a reduction in executed cycles. Based on our discussion so far, we propose a method for estimating a reduction in executed cycles from a reduction in miss regions. A reduction in executed cycle is estimated by this expression. The first half of the expression is a constant determined by each program. The second half of the expression is a reduction in miss regions. Using this expression, the approximate performance of a modified instruction cache design can be estimated rapidly. This is 2 orders of magnitude faster than a full simulation. Please see our paper for details. We estimated the performance when applying instruction prefetchers. We used 50 traces distributed in the first instruction prefetching championship as workloads. We used the championship to simulate a processor. To simulate realistic branch target prediction, we added the branch target buffer and the return address stack. This table shows the error rate of cycle per instructions estimated by 2 methods. When any instruction prefetcher is applied, the performance estimate using our proposed method is more accurate than the performance estimate using a reduction in instruction cache misses. I will conclude our presentation. We introduced the idea of a miss region, an appropriate metric for designing an instruction cache. We proposed a method for estimating the performance when modifying the instruction cache design based on the number of miss regions. Our proposed method accurately represents the performance of a processor applying an existing instruction prefetcher with an average error of 1.1% and a maximum error of 4.1%. Thank you for your listening.